Okay. Yeah, so I think we should move into 15.4. This pen doesn't work too well. Yeah, that's better. Okay, so 15.4 is about Green's theorem. So let's talk about it. But hold on just a second. So what did we learn last time? In 15.3 we learned that we're working on this integral. But what we learned is that over a curve, right, we're working on this integral, which is the work done by the vector field on a particle as it travels this path c through the vector field. So this is the work done by the force field or vector field or force field, blah, blah, blah. So we learned that if F is conservative, then we got some options. What we learned in 15.3 that if F is conservative, this thing is independent of path. So sometimes you can pick a new path, or you can find the potential function and evaluate it from the end point and evaluate the beginning point and subtract the difference. It's kind of like finding that potential difference. And if it happened to be closed based on that potential difference, if it happens to be a closed curve, the answer is 0. So if you're in a conservative vector field, you got a lot of options, and the main thing is that a closed curve is 0. The work done is 0. That's not the main thing, but that's a cool byproduct. Well, Green's theorem is for a closed curve. But if Green's theorem is about a closed curve, then we must be in a non-conservative vector field. Because if it was conservative, that would be pretty boring. A conservative vector field on a closed curve is 0. So if Green's theorem is about a closed curve, we must be in a non-conservative, it works better in a non-conservative vector field. Otherwise the answer is 0, right? So I'm thinking F is probably non-conservative. But here's the deal. If C is a closed path, and I'm going to say, use this funny phrase, and traversed, it's a closed path, traversed, or that's traversed, I'm changing that, oriented, counterclockwise. So, you know, there is an orientation to these curves we've been drawing. There's an arrow and an orientation to where they start and where they end. But if it's a closed path oriented counterclockwise, then, and then I'm just going to add the phrase, F is not conservative, because if it was, it'd be 0. But, so I'm just adding this. But, then here's what Green's theorem says, that this integral that we've been working on could be done like this. This is a trick. You ready? It could be done with a double integral over the region R. And then I got to talk about what the hell is the region R. But then it's the double integral of, what is it? It's the double integral of dn dx minus dm dy. Keep in mind, if it was conservative, this would be a 0 and this answer would be 0. So this is only kind of interesting when it's not conservative. That's about the 5th time I said that today. But it's not a violation. If it is conservative, it doesn't violate anything. It's just 0 and boring. But look at this. Instead of doing the single integral, this work integral that we've been working on can be done with this double integral. dn dx minus dm dy is the integrand. You integrate with respect to A, the area of the region R. And what's the region R? I have to tell you. Where R is the region, R is the region enclosed by the curve C. Which, if it's a closed curve, it will form the boundary of some region R. What's so funny about this is then you're worried about the path C But if it's a closed path and encloses this region R, all of a sudden you don't care about the path. I mean, it isn't about the path, now it's about the region R that is surrounded by that path. It totally changes the problem. This is a kind of a trip. And by the way, this is kind of the last thing we do here. We're in the middle of chapter 15, but we can't get much further. So this is going to have to be it for Cal 3. Let's try a problem. I mean, that's Green's theorem. Now, let's try a problem. So if I open the book to 15.4, I should be able to find a good problem here. Let me see. 15.4. Okay. All right, they can do this. They can talk several different ways. Ooh, that's a weird one. But here's one I found. They give me this vector field. X squared minus y squared, and then 2xy. X squared minus y squared, comma, 2xy. Well, like I guess we're learning here, whether I'm back in 15.3, I guess I should finish these notes real quick. If f is conservative, this integral is independent of path. This integral is independent of path. That's what we learned in 15.3. Which actually, just that idea opens up a lot of options in 15.3 we learned about. And that was the last class. But now I'm trying to do this. But anyway, either way, dude, I need to figure out if f is conservative. That's the first thing I need to do. By the way, the path is this path around the circle x squared plus y squared equals 16. And they should have said counterclockwise. They didn't bother. But in order to use Green's theorem, it has to be going around that thing counterclockwise. Anyway, I need to know if it's conservative or not. Hey, it's a closed curve, so if it is conservative, the answer is 0. This is a circle of radius 4, and we're going to go around counterclockwise. It's a closed curve. I need to know if it's conservative. Here I go, real quick. dm dy, dm dy. Negative 2y. If you lost that negative sign, that would be bad. That would kind of ruin your life, maybe. Maybe not. dn dx. What's dn dx? Yeah, 2y. Right. So kind of close, but no, not conservative. That negative sign, no, they're not the same. So it's not conservative. Awesome. So it's not conservative. It's not necessarily 0. The answer still could be 0, but it's not guaranteed to be 0. And so I think I'm going to do Green's theorem. So what's Green's theorem say? Green's theorem changes the game so where it's not about the path, but it's about the region. Oh man, this is not going to be cool. Yeah, here I go. I mean, I'm going to try to set up a double integral. And then what am I integrating in my double integral? Well, according to Green's theorem, I'm integrating dn dx minus dm dy. Okay, dn dx minus dm dy. So that's a 2y minus a negative 2y. Oh, okay. Yeah, that's what I'm integrating. dn dx minus dm dy minus a negative is plus. Okay, I'm integrating a 4y. Okay, cool. That's this. And then I need to do this dA. So dA can be, dy dx, dx dy, or any other ideas? dA can be dy dx, dx dy, or
dr d theta.
Yeah, r dr d theta. It comes with that extra r dr d theta. Yeah, it could be r dr d theta. I mean, in fact, look what I'm doing. I'm going around a circular curve. I mean, the region is a circle. The region enclosed by this path is a circle of radius 4. I probably want to do polar coordinates. I didn't want to start with that. I wanted to ease into this idea of Green's theorem, but so I was going to do some in rectangular coordinates, and then find a problem that said, let's switch to polar coordinates. But I'm sorry, the first problem I found was a circle. I really want to do it in polar coordinates. So what does that mean? That means my dA is r dr d theta. I need to convert this to polar coordinates. What would be my bounds for r? And now, I'm not going around a path. Try to ignore the path and think about the region. Bounds for r.
0 to 4.
0 to 4. Bounds for theta.
0 to 2 pi.
0 to 2 pi. And then all I got to do is convert this y into polar coordinates. And y is, I think y is r sine theta. Y is r sine theta for any. I mean, that's how you convert. An x is r cos theta. A y is r sine theta. So this whole problem has turned into a whole new game here. This is, I'm not even doing the vector field anymore. Are you with me? I'm doing 4r sine theta times that other r. If you don't mind, I'm going to call that r squared dr d theta. I'm back to chapter 14 doing a good old double integral, which is just chapter 14 doing a double integral. I'm using this double integral to do the work done by the vector field, but there's no vector field in this integral. I've changed this integral, which is the dot product of the vector field, I've changed this line integral into this double integral over this region, thanks to Green's theorem. You're allowed to do that. It's equivalent. So that's the new game, and it might make some problems easier. So we're going to try it. I guess I should finish this one. I'll finish it over here. Integrating with respect to r, I think that would be 4/3 r cubed, and just leave the sine theta there. Integrating with respect to r from 0 to 4, you plug your 4 in at 64 times 4. Everybody knows that's 256 thirds times sine theta. Now we're integrating with respect to theta. This could be a trip here at the end. Let's see what happens. With respect to sine theta, I think you get negative cosine theta. Negative cosine theta. When you integrate sine, yeah, you get negative cosine. This is going to be a trip from 0 to 2 pi. Here we go. When you plug in a 2 pi, that's a 1. So I get negative 256 over 3. Minus, when you plug in a 0, that's a 1. So you get minus another negative 256 over 3. Guess what a negative plus a positive is? 0. This was a closed curve. It was a non-conservative vector field. There was no guarantee that it's 0, so we couldn't say it was 0. We had to do it. It turns out it was 0. That's okay. There was no guarantee that it was going to be 0. It just came out to be 0. Not because of the closed curve thing, but probably because the vector field I'm in, I can't see the vector field I'm in. And again, we sort of turned it into a region problem, the area of a region or volume of a, we sort of turned it into a double integral problem. But we could keep in mind that what was going on was there was a path. We were going counterclockwise, and perhaps the vector field there was, who knows? Maybe from 0 to pi over 2, you did some positive work. Or maybe from 0 to pi, there was a lot of positive work. But then from pi to 2 pi, there was a bunch of negative work. Somehow it canceled each other out, and we got a net work of 0. Or maybe the whole time what we had was perpendicular vector field the whole time. So no matter what we integrated, it would have been 0. I don't really think that's true. Or maybe this was positive work, and then this was negative work, and then this was positive work, and then this was negative work. Somehow, some way, it all canceled out to be 0 work. But there's a lot of reasons why it might have been 0 work. But it was 0. Yes, sir.
Negative work, it's not work specifically, but it's going with the motion of the object.
Let's see, it's the other way around. So when the vector field is kind of with the direction of motion, the integral will come out to be positive work.
Okay.
When the vector field is kind of going against the direction of motion, the answer will be negative work. And it's the work done by the force field on the particle. Yeah. Sometimes I feel like I'm the little particle and I'm swimming through this force field. How much work does it take me to swim through here? But that ain't really the right way to, it's the other way around. It's the work done by the force field on the particle. Cool. Let me try another problem. I'm sorry, that one turned into a good old polar coordinates, which I wanted to bring up some point today. This Green's theorem can be done in rectangular coordinates or polar coordinates, right? This dA could be dy dx, dx dy, or r dr d theta. It depends on the region. It depends on the region enclosed by the path. That circular region made me want to do polar coordinates. And the book words this kind of funny. Here's another one. Here's another one. This happens to be number 12 in the book. I'm in 15.4. And this happens to be number 12, which gives me this integral. By the way, I keep talking about this integral. This is our work integral. You know, last class I told you that sometimes it's presented in this alternative form. The alternative form is m dx plus n dy. That's it with the dot product already done. With your vector field and your dr, and go ahead and do the dot product, you end up with this. So this is just kind of an alternative form for this. But it's really just a step down the line. It's the dot product already done there. So they're presenting it to me like this oftentimes. So number 12. Number 12 is presented like that. Y squared dx plus xy dy. Y squared dx plus xy dy. And then they describe the curve to me. You know, I'd rather maybe sometimes draw the curve. So I'm going to draw this shape. That's the shape. They described it. Rather than describe it, I'm giving it to you here. This is 12. Y equals the square root of x, x equals 9, y equals 0. I'm going to call this 9. And I'm going to point to this curve and call it y equals the square root of x. Hey, I made the arrows go counterclockwise because you got to. If you're going to do Green's theorem, it's got to be going counterclockwise. You know, I'm not sure about why that is. The theory, you know, and I didn't prove Green's theorem to you. It seems like quite a leap, you know, and I didn't prove it at all. So I just believed it. And I believe the fact that they say it's got to be counterclockwise. I do know one thing, though. If you do one of these problems and you have the orientation wrong, not a Green's theorem problem, but just if I was to go do all this work counterclockwise and then do the same problem clockwise, I should get the negative amount of work. So if one of them happened to be oriented clockwise, it should just be the negative of the one that's counterclockwise. But I don't know. To use Green's theorem, it should be oriented counterclockwise, and they usually all are. So I'm not trying to mess with you and negate. That's the way we give them. That's the way we present them. Well, there we go. Closed curve, counterclockwise. I guess I should use Green's theorem, but wait a minute. The answer is 0 if it's a conservative vector field. Let's just check that real quick. By the way, checking to see if it's conservative is not a waste of time, because for Green's theorem, you need this dn dx and this dm dy anyway. You need these for Green's theorem. So let's stop here and check and see if it's conservative. dm dy, there's m by the way. dm dy would be 2y. dn dx would be y. So, not conservative. Okay, cool. If it's not conservative, I'm going to really do Green's theorem. I'm going to really do it. Okay, here we go. I'm going to really do it. I'm going to set up a double integral. What am I integrating? I'm integrating dn dx minus dm dy. I'm integrating dn dx minus dm dy. That's a y minus a 2y. You got to make sure you, excuse me, subtract that backwards. And now I got the dA. The dA is, again, dy dx, dx dy, r d theta. So we already did one today that we wanted to switch to polar coordinates, and we did. I don't think I want this one in polar coordinates. Look at the region. The region is not good for polar coordinates. The region is good probably for dy dx, don't you think? So dy dx. So can you tell me the bounds for y?
0 to the square root of x.
So y goes from the bottom, called 0, to the top, called the square root of x. I think so. 0 to the square root of x are the bounds for y. And then the bounds for x are?
0 to 9.
0 to 9. That is a 9. 0 to 9. Cool. That's it. It'll be the area, it'll be the volume under this surface over this region. I mean, yeah, that's how we talked in chapter 14. Now in chapter 15, this double integral is not area or volume. Well, it could be considered area or volume, but this double integral is the work done by, it's this integral. This integral can be done with a double integral. That is cool, man. That saves me so much time. Again, I don't know how many problems I've done with you, but to do this without Green's theorem, you got to do C1, which ain't a very hard path. You got to do C2, which is an easy path. You got to do C3. I mean, you got to do 3. You'd have to set up, you'd have to do 3 of these and add them all together with your 3 different little paths to figure out what this is. So we could do that, but boy, Green's theorem, this is easy. Here we go. I'm going to try it now. This y minus 2y turns out to be, you know, a negative y is what that is. When I integrate it, I guess it's negative y squared over 2. When I plug in my bounds, 0 and the square root of x, this is really nice because I plug in the square root of x and I square it, so I get x over 2 with a negative sign in front of it. Wow. So this Green's theorem just turned into negative x over 2, and now I'm integrating it from 0 to 9 with respect to x. Is that what just happened? Hang on. This is a negative y. I integrated. Negative y squared over 2. I plugged in my bounds. That's what I've got. Now I integrate again with respect to x. Okay. The negative sign's out front, so it's out front. So it's negative x squared over 4 when you integrate. From 0 to 9 is whatever. I guess you plug in your 9. I guess you get a negative answer here. Negative 81/4 is the answer. There's nothing wrong with a negative answer. When we do these work integrals, it could be negative or positive or 0. It could be anything. Cool. That's my answer. That's it. That was easy. Green's theorem is so nice. So nice, so nice, so nice. Let me try another one. Let me try this, not that one. Where's this? I saw one in here. No, not that one. Okay, here's one. Here's another one. number 8. So I'm in the homework. I'm in 15-4 doing a little homework. This is number 8. I like this one. This one maybe is, they say to do this integral. It's a line integral. Y minus x dx, plus 2x minus y dy. Plus 2x minus y dy. Okay. All right, cool. They want me to do that integral. Now what, over this curve, along this curve, now what's the curve? The curve is described as, number 8, x equals 2 cos theta, y equals sine theta. I prefer to use t. They said x equals 2 cos t. They use theta, I use t. And y equals sine t. All right, well, this is a parameterized curve. And so, what is this parameterized curve? Do you know what that is, you guys? It's very typical to let x equal cosine, y equals sine. When you let x equal cos and y equals sine, that's a circle. It's a circle of radius, whatever the leading coefficient is. Oh, wait a minute. If it's got 2 different radiuses, it's an ellipse. So in the x-axis, it's going out to 2 and -2, and then on the y-axis, it's going up to 1 and -1. Yeah, this is an ellipse. Because they used cosine and sine, it is counterclockwise. It's sort of starting here and going counterclockwise, and it's, like I'm kind of weird when I talk like this. It's a circle with a radius of 2 in the x direction and a radius of 1 in the y direction. Well, that's not a circle, that's an ellipse, right? Radius 2 in the x direction, radius 1 in the y direction. Okay, all right. Well, again, it's a closed curve. Dude, if it's conservative, it's 0. I better check to see if it's conservative. What is dm dy? 1. What is dn dx? 2. All right. Okay, cool. Not conservative. That's okay. Not conservative. All right, so it's not conservative. So one other thing. My brain, I got a lot of stuff in my brain but if it's not conservative, I don't have any options. I just got to, well, wait a minute, I do. I got this new option called Green's theorem. Right, if it's not conservative, I don't have those other old options. I can't pick a new path. I can't do the potential. I can't do all that crap. The only thing I can do if it's not conservative is just do it, or maybe if it's a closed path, I can do Green's theorem. And if it's a closed path counterclockwise, I can try to Green's theorem. I think I'll do Green's theorem. If I set up Green's theorem, there's going to be an issue here, though. I'm integrating over this region, and it's a goddamn elliptical region. What am I integrating? I'm integrating 2 minus 1 dA. So here I am using Green's theorem. But ellipses are bad. Ellipses are bad in any world. Maybe that sounds prejudice against ellipses, but they're not fun. And so that means I can either try to do this in rectangular coordinates, which means I need the rectangular coordinates of this ellipse, and that ain't gonna be fun. And I could try polar coordinates, but we haven't messed with polar coordinates of an ellipse maybe ever, or in a long time. Polar coordinates are great for circles. They might be, polar coordinates might be helpful with ellipses, but it's still a little bit nasty conversion from an ellipse into polar coordinates. Because this is 2 minus 1, it turns into a 1. So I am really just doing this integral. And R is this region. And when I see this integral, this makes me think of something from chapter 14. I mean, these double integrals, they were always the volume under the surface over the region R. But at the very beginning, remember, we learned that the book lied to us when they said these double integrals, well, when you're doing a double integral and your z equals 1, you could interpret this as, do you remember?
Area under the curve.
The area of the region R. Under the curve might not be the right phrase. The area of the region R. This again, we called it a lie. We called it the volume of something with a height of 1. But it was the area. When it was a 1, it was the area. By the way, if there was a 3 here, I'd pull out a 3 and it'd be 3 times the area. So this is the actual area of the damn ellipse. So if anybody knows that, we'd be done with this problem. Otherwise, it's the area of this ellipse is what it is. That's the answer to this problem. And I'm saying I can't do it. I'm saying I'm not going to set it up and do it in polar coordinates. I'm not going to set it up and do it in rectangular coordinates. I just wish I knew if I just knew the area of the ellipse, I'd have it. Do you guys know the area of the ellipse? You should know it, especially for this test. This might come up. Well, check this out. When you have a circle that's radius r, what's the area? Pi r squared. Watch how I'm going to write this. Pi r squared, but I'm going to write r times r. What if you have an ellipse that sometimes you hear me say has 2 radiuses, which is bullshit, but anyway. And there's A and there's B. Guess what the area of an ellipse is? A times B. It really is like it has 2 radiuses. That's cool to know. That's cool to know, and I'm going to use it right here. The answer to this is the area of an ellipse, which is pi times its 2 radiuses. One of the radiuses was a 2, and the other radius was a 1, so to speak. The answer is 2 pi. Pretty cool, huh? You want 12 of those problems on the test? Those are easy. Circles, ellipses, squares. What made it easy was this came out to be a number, and not just a number, but the number 1. So it really was area. A few minutes ago, this problem was an area. Oh, back here, a few minutes ago, the answer to this was not this area. Because why? Because there was a function here. The function was a negative y. We were integrating over the area of this region, but we were integrating some function over the area. If that function would have been a 1, we could have called it the area. But because there were some variables here, some functions here, this was not area, and we had to kind of really do it. But dude, this was area of an ellipse, and I'm glad I memorized the formula. So I'm done with this problem. Yes, sir?
What if the x side of the vector f happened to be e to some function of x's and y's? How do we do it then?
Well, okay, so you're changing the vector field. Well, right. See, you may be making up something we can't do, because I just complained about all the complaints. I had a lot of complaints about this problem. But what made it nice was the fact that it was just area. And the area of an ellipse, I have a memorized formula. And so, in a way, I'm not even doing a double integral. I mean, now I'm just using geometry to help me with this problem. Right. So anyway, so you changed this, and then you've changed this, and then you've changed what I'm integrating. And then I got to try to fight through it, either in polar coordinates or rectangular coordinates, and it wouldn't be fun. I mean, if there's a variable in here. But, you know, if this came out to be, I mean, I could switch this up and have it be, you know, if this came out to be 13 minus 8, then what is that? 5. And would it be area? Well, no, not really. It'd be the volume underneath something that has a height of 5. But if it's a 5 and you just pull it out front, then okay, it's 5 times area. And so now it's 10 pi. Right, so then you would, so that if it's a constant that you could pull out, it's those variables that make you integrate it. I mean, then you got to integrate it. It's variables.
So, could you say, I mean, with Green's theorem, could you say that the lateral surface area of a solid is equivalent to its volume?
I don't know. It sounds like you're mixing up ideas, because where does lateral surface area come in? When you said use that phrase, that makes me think of this. That makes me think of lateral surface area.
You're right, I was wrong.
Okay. Right. So this is a different line integral. You could call it lateral surface area. You could call it a lot of different things. It might have some different meanings. It was definitely way less important than this one. This ain't lateral surface area. This is the work done by the force field on the particle as it travels the path. So this is, in 15.2, we learned about 2 different line integrals. As soon as we left 15.2, the rest of this chapter is about this one. Don't ignore this one. He might show up on a test. He might show up on a quiz. But he ain't this, and therefore he ain't this, and he ain't Greek, right? Okay. No, so what you can say with Green's theorem is that the work done by a force field turns out to be the volume under this, whatever this is, whatever, I mean, it's the volume under this, it's not the volume under the force field, or, I mean, it didn't, right? So you can think of this integral as volume. I don't know. I'd kind of maybe
Not.
Maybe not. Just say that this work integral on this force field can be done with a double integral, a specific double integral. Yeah. That's integrating the area of the region enclosed by the path. It is a trip how it works. Here's another one. I hate to take all your fun away. I'm going to try, let's just jump all the way up to 44 and see if we can fight our way through 44. Maybe it's tough, maybe it's easy, but I'm going to do this. 44, Green's theorem, region with a hole. It says, let R be the region inside the ellipse and outside the circle. Okay, they've drawn a good picture of this for me. And then they want me to evaluate this line integral. Okay, so this line integral is 3x squared y plus 1, x cubed is 4x, 3x squared y plus 1 dx plus x cubed plus 4x dy. Now, the region, or the curve, C, that they've given me is quite complicated. They gave me a C1, which is, a C1, which is 4 cos t, 3 sine t, which is x equals 4 cos t, y equals 3 sine t. Then they gave me a C2, which is, 2 cos t, 2 sine t. Now wait a minute, did they really do that? Yeah, they did. All right, hold on. They're screwing up. I think they screwed up. I think I'm going to change this. I want this one to change. I want this to be 2 sine t and 2 cos t, and maybe I'll explain why in a second. I don't like the way what they did. All right, man, this is a tough problem. All right, so we just had a big discussion about what this stuff is. What is this? With the 4 and the 3? What is this? Thank you, an ellipse. So hang on. And like I said, they were nice enough to give you some pictures. But pretend you didn't have any pictures. If you were on my test, you might have to just work with this. So this is an ellipse, and it goes out to a radius of 4 in the x direction, and a radius of 3 in the y direction. And okay, look at when you let x be cosine and y be sine, then it sort of starts here and goes this way. So it is oriented counterclockwise like we want. Now look at this guy. This is a whole different dude here. This is a radius 2, and it's a circle. Radius 2, circle. And not only that, but I put the sine and the cosine opposites so I want it going the other way. It's going this way. It's going clockwise. And what I'm looking for is, well, these are my paths. I got to travel around these paths in this vector field. I got to travel around those paths in that vector field. Man, this might be tough. This might be tough. Who picked this problem? Travel around those paths in this vector field. Well, is it conservative? I got to figure that out. What's dm dy? dm dy. That's what I need. Is it conservative? What's dm dy?
3x squared.
3x squared. dm dy is 3x squared. Okay. What is dn dx?
3x squared plus 4.
3x squared plus 4. Okay, cool. Cool. That's kind of cool. So is it conservative? No, it's not conservative. They have to be equal. It's kind of close, but no, not conservative. All right, cool. So if it's not conservative, I don't have any way to cheat or any shortcuts to take. I have to do Green's theorem, maybe. Maybe I'll try Green's theorem. Do I have a region enclosed by these curves? Yeah. I think the region enclosed by these curves is the region between the two curves. You know, you wouldn't say this is the region enclosed by the curves because that makes the first curve insignificant. So it does have to be the region between the curves. It really does. But, you know, aren't we supposed to have connected paths? I mean, what I'm doing is I'm cruising around this path, and then I'm just cruising around this path. I mean, I think they're supposed to be connected. So watch what I do here. This C1 is this path. This is C2, but I want to connect them. So watch what I do. C1 is going to go around here, and when it gets back here, watch what it does. It's going to go in here. In fact, remember, I started here. Try to keep that in mind. I started here, I went around, I got here, I came in. Now, I want to go around clockwise, actually. Why clockwise? I'll tell you. And then when I get back to here, then I'll go back out. And the work coming in and the work going out will cancel each other out. But at least that'll get me out to where I started, which will make it a closed path. See, now it's a closed path, and it is oriented counterclockwise. Here's the thing about counterclockwise that's a little funny. Why? Geez, this is a little tough, but look at me, what am I doing? I'm going around this region. See this region down here? I'm going around this region. Am I going counterclockwise?
Yes.
I am going counterclockwise. One thing I know, one good definition of counterclockwise is that the region that you're going around always lies to the left. That's a definition of counterclockwise, is that the region lies to the left. So when I came in, that's why I had to go, quote unquote, clockwise to get that. This clockwise ain't clockwise. This clockwise is counterclockwise because it helps my region lie to the left. So I'm defining counterclockwise as the region lies to the left, and we needed this to go this way to get that to happen. So I feel like I have a region between these two curves that is traversed, that is surrounded by a curve that's going counterclockwise. So I'm doing Green's theorem. Jesus. Here we go. I'm doing Green's theorem. And what is Green's theorem? It's this double integral over this region R, and it's dn dx minus dm dy. So it's this 3x squared plus 4 minus this 3x squared. Those are going to cancel, and I'm going to be left with a 4 dA. And like I said, I don't think I really want to do this problem. I don't want to do it in polar coordinates. I don't really want to do it in rectangular coordinates. Because this came out to a 4, I'm so happy. I think I'm going to just pull the 4 out and interpret this problem as the area of my region times 4. The area of my region times 4. And what is the area of my region? I'm going to do a little talking here. I think it's the area of the ellipse minus the area of the circle times 4. So here we go. This is how you finish this problem. After all that talking and working, it turns out to be nothing to it here. Here we go. The area of the ellipse, pi times AB. Oh yeah, hold on. It's my ellipse. A is 4, B is 3. It's pi times 3 times 4 minus the area of a circle, which is pi r squared. My r is 2, I think. Yeah, my r is 2. 2 squared. Yeah, the area of the ellipse minus the area there. Cool. That's a 12 pi minus a 4 pi. 12 pi minus a 4 pi is an 8 pi. 8 pi times 4, and you might get sick. Get it? If you ate a bunch of pi times 4, you might get sick. You know, some of these jokes are like 10 or 15 years old. I've been telling them every semester for years. But that one right there was a brand new one, just in case you were curious. 8 pi times 4, you might get sick. That's a good one. That's a brand new one. Dude, we did it. Woohoo! We found the volume, whatever. What did we do? We found the work done by this force field on a particle as it travels this kind of complicated path around here, in here, around here, and back out. The work done. Cool. All right, listen, I've wandered around here with 3 or 4 cool Green's theorem problems in 15.4. That's, and I've hit the major points, so I don't have much more to say. Is there anything on this take-home quiz you want me to help you with? Is there requests anywhere?
No, I think you solved 6.
So you were worried a little bit about 6. Oh, well now you know, that's true. After today's lecture, there's some stuff that, there's some Green's theorem problems maybe that you can do now, or,
And then 7F is conservative.
You were worried about 7, but I helped you with that earlier today. I think 8's got a couple issues. You know, I think you got to do some quotient rules there. Look at that. Did you see Like number 6 has this vector field here. Look, and if this is m, you got to do dm dy. If you're going to do dm dy, that's a little quotient rule there. So there's some work involved. No pun intended. Yeah, there's 10 of these problems. I'm going to randomly grade 4 for a quiz grade. So this is due Friday. The test is Friday. And we'll be done. We got Wednesday to wrap up any ideas. Okay. I'm going to hit off on this. And maybe we're done early today.